Hello and welcome to the first video in the I2C series. This first video is going to cover some of the basics on the I2C protocol. I2C or I2C stands for Integrated Circuit, and in its simplest form it is made up of a master and a slave. The master and slave share what is called SCL and SDA, which stands for serial clock and serial data. This protocol is bidirectional, meaning that the master can talk to the slave and the slave can talk to the master. The data and clock line each have their respective pull-up resistors, which are shown as R1 and R2. A real-world example of the I2C protocol being used can be seen between a camera sensor that represents a slave and a processor. The processor may want to do a variety of things with this camera sensor. It may want to set settings, begin camera streaming, stop camera streaming, or maybe read a status register on the camera sensor itself. The I2C protocol is valuable because it has a low pin count, only the data and the clock line, and it is very widely used across the industry. This schematic shows a detailed view of the data line on a hardware level. As you can see here, this configuration is called open drain setup, and it refers to a type of output which can either pull the bus down to either ground or a low value, or it can let the bus be pulled up by this pull-up resistor here. This is important because on the I2C bus, you can either have a 1 or high value or a 0. By default, the I2C bus is held high. If the slave or master would like to communicate and generate a low value, shown here, what it needs to do is it needs to activate this switch here. Activating this switch here allows the current to ground, meaning at this point here, the value would be read as a logic low or a 0. Once the master or slave is done holding the bus low, it will disable the switch shown here, keeping the voltage value high here, no longer grounding it. What this will cause is this will cause the voltage to raise back up to the logical high level, which would be generated as a 1 shown here. So you can see here the bus originally starts out as a 1. Once the switch was engaged, it allowed the current to ground, dropped the voltage to a logical low or 0 value, and then once it was done, it disabled the switch, keeping the voltage high and generating a logical 1 value. Now that we've seen how highs and lows are generated on the I2C bus, we can go into a little more detail. One of the main things that happens in every I2C transaction is a start and a stop condition. The start condition is defined when the clock is high and the data drops, and the stop condition is defined when the clock is high and the data line rises. Now we're going to get into more detail later on how what happens during the data transfer phase, but the important thing to notice is the start condition, data dropping when clock is high, and the stop condition, data rising when the clock is high. Here you can see how a message is sent using the I2C protocol. Before we saw the stop and the start conditions. This is what's shown here. This initiates the message. You have a start condition and you have a stop condition. The next thing that's sent on the bus is the address frame. What this is either 7, usually, or 10 bits that define which device the master is talking to. So the master will say, hey, we'll send the 7 bits of the slave that it wants to talk to, and then it'll send a read or a write bit. If it sends a 0 in the write bit, that means that it wants to write to the slave. And if it sends a 1, it means it wants to read from the slave. What happens after this first part is sent is that an acknowledgement is waited from the slave. If there is a 0, that's considered an acknowledge. If a 1 is received, it means that the slave did not acknowledge and the transfer fails. Once an acknowledgement is received from the slave, the master then sends the first data frame that is 8 bits long, or 1 byte. After every 8 bits, an acknowledgement is required from the slave to ensure that it received the message. Another data frame is sent of 8 bits here, and another acknowledgement from the slave here, and then we reach our stop condition. Attached here is a very simple I2C write transaction. The gray means that the master is controlling the line, and the white means that the slave is controlling the line. As we saw before, we have our start condition. We have our 7-bit slave address. Now, as we know in the I2C protocol, there can be multiple slaves on the bus. You can have one master with multiple slaves. This slave address is pointing out and saying, hey, I want to talk to this specific slave. This is indicating here that we want to write to that slave, and then we're waiting for an acknowledgement from the slave itself. From there, we know that after every 8 bits, there must be an acknowledge, whether it's data being transferred or it's something specific like a register address. Now, how does this work? Our master called out the specific slave. Out of all the different slaves that are on the bus, this is the one we want to talk to. On that bus, this is the specific 8-bit register that we want to address. Once we confirm that with the slave by receiving the acknowledgement, we then can say this is the data, the 8 bits of data that we want to write to this register address here. Once that's done, we also receive an acknowledge after those 8 bits from the slave if it was successful, and then we have our stop or ending sequence here. The next example I wanted to show you was actually probing a real I2C bus on the scope. And so I found this capture online of a write, and I thought it'd be very useful to try and take a look at one that exists in real life. And so as you can see here, very simply, both lines by default are high, right? So you can see the top one is obviously the clock line because it oscillates, and then the bottom, the pink one, is the data line. They both default back to high, which is what the I2C standard says. Now we can see here our start condition, right? As the clock is high, the data drops. And so the first thing we start with is our 7-bit address. So we have 0011, 0, 1, 0. This is our slave address. Then we see here a 0 was sent on the bus. This means that we want to write. And as you can see here, this is something that a lot of people don't know unless they're in industry. These really low grounds are the acknowledges on the bus, right? So we saw those 8 bits there. We saw an acknowledgement. This here is the register on that slave. So it's 0000, 1010, and then after those 8 bits, we see another acknowledgement. After that, maybe this is a data value, 0000, 10001, and then another acknowledgement, and then our stop condition. And so one of the best ways you can see this if you have the opportunity is to connect your scope to the I2C bus of whatever device you're looking at. Take a credit card and line it up against the rising edge of the clock and see what data value it lines up with. From there, you'll be able to read each individual value. Now, it'd be a lot easier if you had a protocol decode and you could just decode these values in hex or binary. This wraps up the end of the first video of the I2C series, and as the videos progress, we will be adding more detail and going into more specifics.